Hello, everybody. Today we're going to be talking about inequalities. And inequalities sounds like a technical math word, but if you break it down, we're really just talking about expressions that are not always able to be answered with something equaling something else. And there's a lot of times that this pops up. We're going to start with in just a moment with some examples that have real world context where more than one problem has more than one solution. And this might sound a little bit strange to some people because they're used to math being when you get things right and you get to the answer. But inequalities kind of challenge that idea a little bit and say sometimes the answer to a situation, to a model, is a number of different answers. For example, if you're trying to, let's take a look at some of these examples that I pulled up. And if you have this in your notes, go through and for right now, just recognize which of these you think is the most interesting situation. You don't have to worry about solving it. We'll do that in a little bit. But right now, I just want you to think about how would you answer some of these scenarios. For example, suppose that you rented a forklift to move a pallet and you've got these 70-pound blocks that you're going to be stacking on that. Sometimes you can only lift so much due to safety reasons or due to the mechanism. And so if you have 50 pounds accounted for by the pallet, how many of these blocks can you actually put on the situation or onto the machine? These are problems like I've had to deal with when working in warehouses and with manufacturing plants. These safety concerns really pop up and you need to figure out what's the throughput going to be given all this constraint. Or consider instead if maybe you're going into sales. You've got an online retailer here who sells these toys, and the toys are purchased at a certain price, they're sold at a certain price, and the business owner has a certain amount of cost that they're responsible for every single month. How many of these toys do they have to sell? What does it look like to be able to turn a profit and to own a successful business given all these constraints? Obviously, there's going to be a lower amount of toys that you can sell, but there's also a whole bunch of high amounts that would probably work out for this situation as well. What if instead you're trying to compare something like you have a wireless phone company who's offering a monthly plan, and there's a certain number of gigabytes that you can purchase for a certain amount of price, and you're trying to figure out what's the playroom that you have within this plan before you max everything out. Or what I like to kind of look at is this last one. This last one's of real interest to me. Suppose that instead you were looking into construction, or you had a rectangular fence that you're trying to build. You have at least 80 feet of this material, and you know that you'll have no more than 140 feet that's maybe purchased by the consumer, or that you're being given from the supplier. And you've got a couple of these dimension requirements. What's the width? What are the range of length values that you're able to have? What are the possible situations that you can give to the customer, you can give to your employer, you can give to the supplier, given the ambiguity of not knowing exactly what you're going to build yet? When you think through all these different ones, a nice way for us to model this logic is by thinking of the numbers that would be possible for this situation as all being into a pile. And we're going to see that in just a second. We've got some notation that helps us to kind of organize our thoughts on that front. So, for example, let's go ahead and take a look at some of these other situations that you might have used piles of numbers or sets before in earlier math classes. I'm going to go through this one just a little bit quickly because you should have already had this exposure in another math class. And in the case that you haven't, you do have the ability to go back in your textbook to look at R.1 and to familiarize yourself with this. But I want to do just a really quick review of 3 different ways that you're probably familiar with talking about groups of numbers. One of them would be on this number line. So this is going to be the real number line. The real number line, again, if you recall, has a bunch of different things that go into this real numbers category. You've got your natural numbers, your counting numbers, the ones that nature understands, like 1, 2, 3, etc. You have your whole numbers. Your whole numbers are going to be all of the numbers that are natural and the number 0. These will be your full entities, what we're going to call our whole numbers. Represent all of these with letters that have an extra little leg or an extra bold spot on them to help to show that we're talking about piles and categories with these letters, not just a single variable or a single letter. So we've got the naturals. These are our counting numbers, our nature numbers. The whole numbers include 0. You have your integers. Your integers are normally represented with a Z, and that's for the German word for numbers. but z is going to be all of your whole numbers and then the negative versions of those as well. So your -1, -2, -3, as well as your -0, but that would obviously just be 0. You have quotient numbers, your rational numbers they're often called, and we represent that with a q. So rational numbers would be any number that you could represent as a fraction where the top and the bottom are either whole numbers or integers. So you have your quotient numbers, your rational numbers. You also have your irrational numbers. Your irrational numbers are all the numbers you would not be able to express as a fraction using integers on the numerator and the denominator. These would be like your pi, your square root of 2, your cube root of let's say 9. All of these different numbers that we know can pop up, but that aren't necessarily easy to represent as fractions. And if we type them into our calculator, we get decimals that go on forever and that don't repeat. Okay. So all of these together make up what we call the real numbers. And so I'm going to give you a nice easy way to think of the real numbers. The real numbers are all numbers that you could imagine putting onto a line and that correspond with your positive and negative lengths. So this is going to be your ones, your negative ones, but it's also going to be your 1/2, your -1/2 that are involved in the rational numbers. You're going to have some square roots of 2 that are going to pop in here. You're going to have your pi values that are going to pop in here. These are all length numbers or negative length numbers, and we're going to refer to those as our real numbers. So whenever I say real numbers, we're talking about all these different things that could be considered and that are all together make up the pile of real numbers. Now, the advantage of using a number line is that we can represent using a picture these intervals or these chunks of the number line that we really want to consider in our answers. So as a real quick refresher, whenever you have an interval, that means that we're using 2 different reference points, one being A and one being B. And we're talking about between those reference points, all of the numbers are solutions to our situation. So we could say that, for example, if I gave you parenthesis 2 and 3, that means all the numbers between 2 and 3 are solutions to my problem. The question quickly arises, what about at the number 2 and at the number 3? And this is a normal human question, and if you don't believe me, try to talk with a 2-year-old or a 5-year-old and tell them where it is that they need to be in the driveway so that they don't get in trouble. Almost immediately they're going to want to challenge that, and they're going to put their toes against the line, and they're going to challenge to say, well, you weren't clear, perhaps I was still in the driveway, I was just at the edge of the driveway, is that still not right, is that wrong? So whenever we're talking about these intervals, we want to be very careful about, do we include the reference points, these endpoints, or not? A more, we'll say, serious or critical example of when it's really important to focus on these details is, consider that you were trying to advise a business and you said that at $3,000 the business needed to declare bankruptcy. Well, does that mean when they have $3,000 in the bank, does that mean that you need to be above that $3,000 mark? Does that mean the moment it hits $2,999, that's the first time that you declare bankruptcy? That's a very important detail that could make the difference between a business staying in business or closing their doors. So you have to talk about what happens at those endpoints and be very clear. For us, we're going to talk about them using a couple of different ways of writing our notation, depending on what serves us. The first thing I want to talk about are these parentheses. These parentheses are going to be our way of kind of softening this reference point and showing that, yes, that a reference point is a reference point and it's going to help us to chunk out this number line, but parentheses means that a itself is not included. So in my example over here, 2 would not be in the pile of numbers that work for my solution. Similarly, b, because it also has a parenthesis, would not be included. Now, one way that we could write that a little differently that's maybe a little bit more familiar is using what's called set builder notation. And set builder notation, if you break down the words, set literally just means pile or grouping of numbers. It's a pile of numbers that work for this situation. So if I'm talking about all the numbers between 2 and 3, but not at 2 and not at 3, I could talk about the set, that's what the curvy bracket means, the set, the pile of all numbers, no matter what they are, so we'll use X, such that, that's what this straight up and down line means, such that. So it's the pile of all numbers such that those numbers are between 2 and 3. And so we would write that using less than and greater than to show that we're not including 2 and we're not including 3. So just to kind of add to your notes here, you can put in here that these curvy brackets here, this means set or pile of numbers, and this straight up and down line here means such that the following conditions hold. Well, quickly we can see and make sense of all of these other notations as well. Our brackets then are going to be our hard inclusion. In our picture, we're going to close in our circle around A to show that that means that we're including A and that we're including B. Same thing with B. And for our symbology, we would use less than or equal to show that we could be all the way up to B and include it, or we could be all the way down to A and include that one as well. There's nothing to say that we wouldn't have different conditions depending on if we're talking about A being included or B not being included, so there's no reason we can't mix and match our parentheses and our brackets to say that maybe I need to be above A, but if I'm at B, it's still okay. And then lastly, we want to talk about this use of infinity. Infinity is not a number, and this is important to note. We were just talking about real numbers. Real numbers are all numbers that correspond with length, and you don't have a number that's infinity, and you don't have a length that's infinity. This is an idea. In fact, it's an idea that's been causing fights and arguments for hundreds and thousands of years. In fact, in religious circles and mathematical circles, arguing about infinity is a really deep topic. So when we say infinity, we're not talking about a number. And if you think it is a number, I'm going to ask you to go out and measure it. It's very, very difficult to do. You can't do it. It's not a length number. So instead, we just use it as a placeholder to mean I can't put a number here. And if I tried, I would need to talk about the biggest number that possibly could ever exist. So that's going to be why when we include either positive infinity or negative infinity in this notation, we're going to have to use parentheses. And we use parentheses because, again, if you tell me infinity is included, I'm going to go ask you to find it. And that's an impossible task. So infinity gets parentheses. When we use our notation, we don't actually even need our set builder notation because I just am going to use my lower a as the reference point and say all values greater than a are in this pile. Okay. That's enough of the review for that. Let's do a quick little example to help kind of anchor it in. So we've got this picture. We're looking at all numbers that are between -6/5 and 3, meaning that I'm looking at an interval. So identify the type of interval. This would be a half open interval because one of the endpoints is open. So let's call that a half open interval. We could write it using set builder or pile builder notation. That would mean that I have a set of numbers, and I'm about to describe them for you. So I have a set of numbers such that all of these numbers are between -6/5 and 3. So I can say that x needs to be below the 3, above the -6/5, and because the 3 is shaded, I could say it could be less than or equal to the 3. So the last thing to do is to write this interval notation. Interval notation would say that my reference points are -6/5, and 3. Do I include -6/5? I do not. It's an open circle. So we'll use parentheses to show that it's a reference point, but that I can't actually include that. That's not one of the numbers in my pile that helps make my statement true. What about 3? 3 is included. We'll use a bracket to show that that is something that is being included, that we're being very clear about including that and making that a hard inclusion. All right, let's see what we can do, and perhaps again, this is a little bit of a review, so I'm going to move through it quickly, but this idea of unions and intersections. Unions, just like the word implies, is talking about bringing two things together, like a marriage union. Intersection, however, just like if you were thinking about a Venn diagram, is looking for where two things overlap. It's just the middle there. So when we're talking about that in terms of these number lines and these intervals, we can help to organize our thoughts again using pictures. The first thing is that we have in parentheses that we're going to be unioning this -infinity to -2, and then the -2 to infinity. So let's draw that out using our pictures. In my number line, I'm going from -2 to -infinity, or the other way of thinking about that is all numbers that are less than -2, but I don't have another number that's my stopping place for it, so I put -infinity instead. So on my number line, let's go ahead and put that in. We're going to have let's see, -4, -3, -2, -1, 0, 1, 2, etc. So I'm kind of just marking off my number line and remembering that even though I'm marking my integer numbers here, that really all of the numbers in between are included in my pile. Okay, So let's see what I can do. I've got negative infinity and -2 as my references, but that just means to the left of -2. Okay, then I'll start at -2 and I'll run all the way to the left. Do I include -2? I do not. -2 has a parenthesis next to it, so that is not something in my pile, so we'll keep an open circle there. I'm unioning that. I'm going to join that with the interval between -2 and infinity. So let me go ahead and write that using green as well. Since I'm unioning them together, I'm creating the same pile with those. That means I start at -2 as my reference point, and then I go all the way until I go to infinity. Oh, but I can't get to infinity, so really I'm just saying I'm going positive more and more. That's going to be the yellow part of my picture here, is all this, I guess I should have drawn it in yellow, but I did it in green. So we've got all of this here. That's our first statement for our union. Wonderful. Now let's see if I can create the other circle like I would do in my Venn diagram, or another picture, and I'll look for that overlap. So in my overlap, I've got again my -4, -3, -2, -1, 0, 1, 2, and I'm going to look to capture all of the numbers that are between -4 and infinity. Okay, so -4 would be, this would be my reference point. And then I'm going all the way positive. And do I include -4? I do include -4 because it has a bracket. So let's go ahead and shade that in. Excellent. Now let's see what the intersection would be. Where is the overlap between these two? Well, is -4 going to be overlapped? Yes, it is. It's in both of my pictures, so I know -4 is going to be overlapped. Is -5 going to be overlapped? -5 is over here. Nope, it does appear in my second picture, so -5 is not included. -4 is my furthest negative reference point. So I'm going to include that one, and I'm going to use a bracket to show that it appears in both the first picture and second picture as a solution. Okay, what else can I go with? -3 works, the numbers between -3 and -2 work. -2 does not work. -2 is not in the above picture. So I'm going to say that -2 is my next reference point that I need to kind of stop at, and I'm going to say that that is something that is not included. Okay. What else do we have? Well, -1 works, but don't all the numbers between -2 and -1 work? Those work as well. So we don't want the next reference point to be -1. We want the next reference point to still be -2, because I'm saying that all the numbers right next to -2 and all the way up to -1 are going to be included. And in fact, there isn't a place that I stop after that, so I'll put infinity. So I've shown that -2 is not included, no matter if you look at the first pile of numbers or the second pile of numbers, but that actually, in order to answer what this entire thing is, requires two different intervals: the interval between -4 and -2, and the interval between -2 and infinity. So you could think of this as saying that I have both of these, but instead of our and symbols, let's use the same symbology we had before. Let's just write in that we are going to union and join these two answers, these two intervals, as our answer. Perfect. Let's see what we can now do with this idea of intervals and piles and set building notation in our real number line to handle problems like this, these inequalities. Inequality, again, meaning that we have things that aren't just equal, they're unequal. They're less than or greater than, equal to, but it has a little bit extra on top of that. So we have inequality, 2x minus 3 has to be less than or equal to 5. What do we think are maybe some appropriate solutions? Should we try some? Let's try the number 10. Let's say, what happens when x equals 10? Well, that would be 2 times 10 minus 3 would be less than or equal to 5, if 10 was a good solution. That would mean that 20 minus 3 is equal to 5, which would mean that 17 is less than or equal to 5. That's not true. Okay, so we'll put a double cross there to say that was a conflict. That didn't work. Maybe x is equal to 5. Would 5 work? That would be then 2 times 5 minus 3 would be less than or equal to 5. That would be 2 times 5 is 10, minus 3 would be less than or equal to 5. That 7 is less than or equal to 5. That won't work out either. Well, I could guess that probably 0 would work. So I've got x is equal to 0 would likely work, because that'd be 2 times is 3 is less than or equal to 5, and 2 times 0 is 0, minus 3 negative. Negative 3 would definitely be less than or equal to negative, or less than or equal to 5. So that one works fine. So instead of trying to do this guessing and checking, how could we be a little bit more strategic about it? Well, let's use that number line. I'm looking for all numbers that are both this expression, my 2x minus 3 has to be the pile of numbers less than or equal to 5. So let's write out a number line. Let's look at, say, this will be 1, 2, 3, 4, 5. This is going to be 5. And we're going to say that all of the numbers that are at 5 or less than 5, so that's all of these, are numbers that are my 2x minus 3. So for example, if 2x minus 3 was the number 2, then 2 would definitely be less than 5, and so that would be fine. I could let 2x minus 3 be the number 2. But that's not helpful. I'm not trying to find out what 2x minus 3 could be. I'm trying to find out what x could be. Okay, so let's see if we can't keep working through our logic. Well, if 2x and then I subtract 3 could be as high as 5, then that means that really 2x could be as high as 8. Because then I would subtract 3 and back at 5. So I could draw another picture to say that the 2x part of this could really be 8 and everything less than 8. And again, if you don't believe me, choose something in this pile. If x was 0, and then I subtracted 3, I would be just fine. So 2x could be everything that's less than 8. Well, then that would mean that x could be everything as high as the number 4, because if it was as high as the number 4, then when I multiply it by 2 and when I subtract 3, I'll still be less than or equal to 5. So that means that my next picture is going to say that my pile of x values is everything that's 4 or less. Well, then that would be the answer to my question, is that x would be the pile of numbers. Anything in this pile would be a good answer for x. Anything that is 4 or less. How can we represent this using our equations or our inequations like we had above? I'll show you. 2x minus 3 less than or equal to 5. What did we do? We got rid of the negative 3 in our thoughts and said, well, what would the 5 transform into to still be a similar expression? Well, we said 2x could be less than or equal to 8. And then x could be less than or equal to 4. And we begin to recognize that these rules that we might have learned about from inequalities are actually just the logic of transforming this picture. I can add 3 to both sides of inequations. I can divide both sides by 2. And that gives me two solutions as x could be less than or equal to 4. And that would my original situation be perfectly valid. Again, if you don't believe me, let's try it out. Oh, we already did right here. X equals 0 is less than 4. And works out just fine. X equals 5 is a number that's big, and sure enough we hit a conflict. 10 is too big, and sure enough we hit a conflict with that one too. So now we found our boundary point, we found our reference point, and we know that x less than or equal to 4 is the full set, the full pile of solutions that work for this situation. Let's look at a situation that might be a little bit more difficult, like this one here. Well, we don't know the context necessarily for all of this in relation to each other. We're trying to use the models of logic that we had to develop shortcuts to help to expand our intuition. So if I'm trying to solve a problem like this, maybe my first intuition is to do the same thing that I would want to have done if I was trying to solve it like there's an equal sign between. Well, let's for example try to get all the x's on one side. So perhaps I add 4x to both sides, and then maybe that would leave me with negative 9x minus 3 plus 4x is less than or equal to 7. Let's get the numbers on the other side. That'd be negative 9x plus 4x is less than or equal to 7 plus 3. That's from adding 3 to both sides. So that means that negative 5x is greater than or equal to 10. Wonderful. Now I have something that maybe I can convert back to a picture. So in my new picture, I have 5x is going to be all the numbers that are greater than 10. So here's 10. 10 is included, and 5x is all of these numbers. All these numbers would be valid numbers for 5x. Well, then what is x? It's some number that I could multiply by negative 5, and my reference point would again be this 10. Well, it makes me think that it would be then -2. So I'll put a -2 here, and then I'll think to myself, am I looking to the right-hand side or the left-hand side? Well, let's check it back forth with our picture. If I tried something to the left-hand side, like -3, would -3 work? -3 times -5 would be +15, and that'd be greater than or equal to 10. That'll work out just fine. So -3 is going to be part of my pile. -2 is going to be part of my pile. And you'll see that if you try -4 or -400, all of those are part of your pile as well. So the left-hand side works, but the right-hand side does. If you chose a number over here, like let's try the number 0, and you put it in right here, -5 times 0 would be 0, and 0 is not greater than or equal to 10. So notice that we found something kind of interesting. When we divide both sides of an inequation here, when we divide both sides of an inequality here by a negative number, we've essentially taken that number line and we flipped it. Here, we had done some shifting where we were shifting things by 3. We're having things to go from 8 to 4. When we multiply by negatives, we're really flipping the entire number line around, and we're making negatives become positives and positives become negatives. And that makes sense, because if I'm talking about taking a pile of numbers x, multiplying it by 5 and making that become greater than 10, it would make sense that negatives times my -5 would become positive, and positives times my -5 would become negative. So I've flipped the direction of this inequality. All in all, what really said that we were able to say the solution is that x is going to be all numbers that are less than or equal to -2. And so notice that my inequality is less than or equal to when it used to be a greater than 2. Now, in our high school math classes, we're often taught that whenever you multiply by a negative number, you need to make sure that you flip the inequality. But it's important to understand where that comes from. You're flipping the inequality because when you're talking about numbers that are in the piles that would work, and then you talk about whether or not they're being affected by a negative, you're really thinking about the opposites of those piles. That word opposite and negative is popping up. Okay. So we have that we can add to both sides, we can subtract from both sides, we can divide and multiply by positive numbers without changing our inequality, we can multiply and divide by negative numbers so long as we have our inequality. And notice that although here we just did division, since multiplication and division are the exact same idea, really I'm saying that if I have to flip when I divide by a negative, I would also have to flip when I multiply by a negative. Again, if you don't remember that, if I divide by 5, that's the exact thing as me saying multiply by 5. Multiplication and division are the exact same thing, it just depends on how you want to look at them. I think we have enough to kind of generalize our findings and solve some of these more difficult problems much more quickly. So, let's take a look here how we would solve this inequality. Well, I know I have my 2. The parentheses, I could simplify those because I'm talking about distribution. And since I haven't yet gotten to my inequality yet, really I'm just saying, how can I rewrite the left-hand side as something that looks different but means the same? And distribution is a rule that I can do with that. So -5 times x would be -5x. -5 times -2 gets me a +10. Then I have my inequality. I haven't changed any meaning so far, so let's go ahead and leave that as it is. And then on the right-hand side, I'll do something similar. 4 times 3 would be 12, and then 4 times -2x gets me 8x. And then I would have +7. Okay, great. We can simplify a little bit more. I have 2 and 10, that's on the left-hand side, so I would write that as -5x plus 12, less than 12 and 7 would combine to get me 19, and -8x would get me a -8x. Oh, let's do the same thing we did in the earlier problem. Let's try to get all the numbers on one side, the variables on the other, so that we can read it properly. That would be if we maybe added 8x to both sides. Or actually, for demonstration purposes, I'm going to choose instead to add 5x to both sides. So let's add 5x to both sides. You could do either, but I'm gonna show you how we're going to practice with flipping the inequality in a moment. So we add 5x to both sides. That leaves me with 12 less than 19, and then -8x plus 5x gets me a -3x. And then if I subtract 19 from both sides, that gets me -7 less than -3x. And so then that would be that x is going to be, well, let's keep it on the exact same side. So if we divide both sides by -3, then that would be -7 divided by -3 gets me a +7/3. And on the right hand side, I would have x. Oh, but we divide it by -3. Let's make sure that we're being careful with our notation here. Let's divide both sides by -3, and whenever we write divide by a negative, that's going to be our trigger that in fact we need to be flipping this inequality, because our picture behind the scenes is really flipping the number line. Whew, not too difficult. We're able to do that one quite quickly. Now, I want to show you what would happen if instead I had chosen not to add 5x to both sides, but I had chosen instead to add 8x to both sides. Okay, so let's pretend that over here I took a different path and I added 8x to both sides. That would have left me with 3x plus 12 is less than 18. And then let's subtract 12 from both sides. That'd be 3x less than 7, which would mean that x has to be less than 7/3. Notice that this is the exact same thing we found either way. X less than 7/3 is saying 7/3 is greater than x. So this is another way of anchoring in the importance of flipping that inequality. When you flip that inequality, it really is just helping to track where that pile is when it moves back and forth. If you have positive x values or positive values that you're dividing by, there's no need to flip that inequality and you're going to get the same answer. But sometimes if you end up having negatives, instead of needing to rearrange things back and forth, you can just imagine moving that pile to a place that makes more sense. Okay, let's do the last three to really anchor in this idea. Here we're going to be working with some denominators, and the denominators being integers. If we're trying to get rid of the denominators, we can treat it the same way we would do if we had an equation. If the denominators are what are bothering us, let's multiply by something that helps to cancel those away. And so if I'm trying to cancel a 5 and I'm trying to cancel a 2, we can use what's called our least common multiple, or our lowest common multiple, to cancel those away. And here's how we do that. The lowest common multiple of 5 and 2 would be a number that could cancel 5 and a number that could cancel 2. That'd be 10. So if I multiply both sides by 10, I should be able to cancel those denominators, which represent division. Need to do it on the right side as well. Okay, 10 times something and then divided into 5 parts would be 2 each of those parts. So 2, 1 minus 4 w's. And then 10 w's that are divided into halves would be 5 that would be in each of those parts. So that'd be 5w. Less than or equal to negative 50. Well, that would then be 2 minus 8w minus w is less than or equal to negative 50. And that means that 2 minus 30 less than or equal to negative 50. We could add, let's subtract 2 from both sides. Subtracting 2 from both sides gets me negative 13w less than or equal to negative 52. And then that would be w would be, if I divide both sides by negative 13. Keeping track there. Negative means I need to flip the inequality. Flipping the inequality is going to be where now on the right hand side I should have, what that be, 4? That looks like 4. So w has to be greater than or equal to 4. When you're going through these problems, again on the test, if you have some time, take a moment, go back through, and do a check. Let's see if all of the numbers that are greater than 4 would actually have worked here. So let's choose a number like 5. Would 5 work? Well, if I plug it back into the original problem, that's 1 minus 4 times 5 divided by 5. Minus 5 over 2 is less than or equal to negative 5, and we're checking to see if this is a true statement. So that'd be 1 minus 20, that'd be negative 19 over 5, minus 5 over 2 is less than or equal to negative 5. And I can tell you already it's going to be, but I want you to check it and put it into your calculator and verify that that's the case. If you do this number in your calculator, you will get a more negative number than negative 5. So this is a valid statement, and we're good to say that as far as a quick gut check goes, at the very least, it's indicating that we did our work properly. Now, when you have some of these problems that have these inequalities attached, there's no reason to say that you can't have more than one condition that's present. And at the very end of the lecture, we're going to see how this can be quite useful in our earlier problems. But the logic doesn't have to change all that much. For example, let's take a look here at our picture. If I wanted to say that this is a true statement and I want to represent it, let's try to do that. I'll create my number line. I'll say that my first reference point is going to be -2. I have a reference point at 5. In between there are going to be all of my 2 minus 4x's over 3. Okay, so these are all of the x values that work for this statement. Well, if I wanted to just simply know what the numerator was, and I wanted to start to peel away at this problem, I would say that the numerator could be all numbers that once I divide by 3, they will fall in this range. What would be the number that when I divide by 3 would get me to 5? And in fact, we'll put an open circle here to really show that we have a less than and not a less than or equal to, which means we need to have a closed circle over here because that one is a less than or equal to. Okay, so we've got a closed circle, we have an open circle, and I'm going to figure out what to have to take the denominator away from this expression. What is a number that divided by 3 get me 5? That would be 15. So my 5 transforms to 15. What number divided by 3 gets me -2? That would be -6. So I can say that the top part of the fraction, the numerator of the fraction, is 2 minus 4x, would be all the numbers between -6 and 15. Because when I divide them by 3, I kind of go up the chain to my original statement, and my original statement was true. Let's keep going. What can I do to get rid of 2? Well, I could subtract 2, and maybe that would be where I move all of my reference points to the left. That sounds a little bit, I'm not quite sure. Let me show you another way we can. I could rewrite this as saying x plus 2, right? That's the exact same expression as -4, or 2 minus 4x would be -4x plus 2. That's using the commutative property of addition. It's just saying that I can take statements, and so long as I keep the negatives attached, I can move the order of those without changing the meaning. Okay, so that means that I have my -4x's. If I'm trying to figure out what that part is, it means my -4x is some number that after I add 2 to it, I will fall between -6 and 15. So what's a number that if I added 2 to it, I would fall over at 15? That'd be 13. Okay, so my 15 is now transformed into 13, and then a number that if I add 2 to it, I will end up at -6. That would be -8. So now my number line of solutions is all numbers between -8 and 13. We have one to go. I'm looking for the numbers, and we'll draw a picture up here. I'm looking for all of the numbers on my number line that by 4, I'm going between 8 and 13. So these are my x values, my final solution values. What number times -4 is going to get me a -8? That'd be a +2. So my -8, my closed circle at -8, now goes all the way over to a +2. And then my 13, what's a number that times -4 gets me a +13? That would be -34. So that'd be where my open circle has now moved. So we got -13 over 4 and a +2 as my new reference values. Is my shading on the inside still? Did I accidentally lose that? Well, we can always test a number. Let's try a number that's easy. Let's choose 0 and say if I took 0 and I multiplied it by -4, would I end up between -8 and 13? Absolutely, so that's included. There's a bunch of numbers that are small negative numbers that are included. Would the number 1 work? Sure, +1 times -4 would be -4. That would fall in my original category. So again, it's all of the numbers that are on the inside. The only thing that I did when I took away that -4 is I flipped this frame and I scaled some things down. Now we have these pictures. Let me show you what it looks like when we were going to be doing all of our work. -2 less than or equal to 2 minus over 3 less than 5. If we wanted to capture what we did in pictures using our symbols, the first thing we tried to do was undo that 3. And that scaled our -2 up to -6. That scaled our 5 all the way up to 15. And so we are left with just the. So you think of this as being the rule or the technique of saying we could just multiply by 3 so long as we do it to everything. Okay, what did we do next? We tried to take away the 2. That caused everything to shift over. That was in this step right here. We shifted the negative to the negative 8 and 5 to the 13. So if we subtract 2 from everything, that's also valid. Negative 8 less than or equal to negative 4x less than 13. And then we're at the negative 4. That was when I divided everything by negative 4. And it caused and scale everything. My negative 8 turned into a positive 2. My negative 4x turned into just x. My 13 over negative 4 turned into 13 over negative 4. And all of my inequalities flipped to the other direction. When you realize that everything we've been working with can be representing the exact same idea so long as we tie it to pictures. Okay, where we've got every tool we should need to be able to handle the situation we were looking at before that have a lot of different conditions. Okay, solve 1 minus 3x greater than or equal to 7 or 3x plus 4 greater than 7. Well, that sounds to me the way that it's reading like I just need to solve one or I need to solve the other. Okay, let's try it out. If I solve the first, that'd be 1 minus 3x greater than or equal to 7. That'd be negative 3x would be greater than or equal to 6, which means that x would have to be less than or equal to negative 2. That's one set of solutions. The other one would be, if I start with 3x plus 4 greater than 7, then I would have 3x would be greater than 3, which would mean x had to be greater than 1. Well, if I just need to solve one or I need to solve the other, that means so long as I've solved one or I've solved the other, I should have a solution that makes my original statement true. Let's represent that as our picture. In my number line, I have all of the numbers that are less than or equal to negative 2. That means a closed circle and everything to the left of negative 2. That's something that works for my situation. I also have all of the numbers that are to the right of positive 1. So I'll put an open circle to show that it's just to the right. And then that's going to be all the numbers that are to the right of positive 1. And if I fall in either this category or this category, then I have solved either the first solution or the first inequality or the second inequality. Well, that just means that I need to include them both. And we're reminded back about our set notation and using that union and intersection to describe everything. We could say that this entire situation could be rewritten as the intervals between negative infinity and negative 2, where negative 2 gets a bracket unioned with x being larger than 1 with no higher bound. So you can express using interval notation how you would capture words like or in the English language. What happens differently when we talk about ands? Well, let's do our quick inequality solutions again. 3x minus 1 is less than negative 7. That's 3x has to be less than negative 6. And then we have x being less than negative 2. Keep in mind that the inequality stays in the same direction. I didn't multiply or divide by a negative. So that's one set of solutions. I then have 4x plus 1 greater than 9, meaning 4x has to be greater than 8, and then greater than 2. So I want to solve both this situation and this situation. Now I'm looking at x values that work for both. So again, in my picture, I'm going to be looking for x values that are above 2, with an open circle at 2 for my inequality over here. And I'm looking for x values that are below negative 2. So put an open circle and say all values that are less than negative 2. Do I have values that work for this and this? I don't. There's not a number that is both less than negative 2 and bigger than 2. So this actually has no solution. And sometimes that's going to be the case, as if we're talking about putting conditions and inequalities. Sometimes if we put too many conditions on it, there's just not going to be a solution that's every single one of the restrictions that we would like to see happen. Well, congratulations, we have everything we need to go back to our original questions and see how, after playing around a little bit in the world of math, we can actually tackle some of these real-world context problems in a nice, organized fashion. I'd like you to do exactly what I'm going to do with the question you chose originally, but I'm going to choose this last question here. The perimeter of a rectangular fence is to be at least 80 feet. Well, let me see if I can sketch that out with the same pictures I was playing with before. It needs to be at least 80 feet. So that means that 80 is my reference point. And is 80 at least 80? Yes. So that means I can include 80 as a solution. Okay, 80 is a solution. It can be no more than 140. Okay, so no more than 140. That means 140 is another reference point. Is 140 no more than 140? Yes. So that would also be a solution. And I'm talking about all of the numbers that are between there. Okay. So this is where the perimeter falls. If the width of the fence is 12 feet, what is the range of values for the length of the fence? Well, I might need to sketch that out. So I'm going to draw a picture. The width is going to be 12 feet. I'm looking for all of the possible length values. So there's going to be a pile of numbers that works for this situation. Well, I'd like to connect my length to my perimeter. So I need to figure out what my perimeter is in terms of length. Perimeter is the length of the fence on the outside, so that would be 12 and then L and then another 12 and then another L if I'm going around this clockwise. So I can say that my perimeter is 12 and L and another 12 and another L. So my perimeter is 24 and 2 of these L's. Between 80 and 140, I need to have 24 feet accounted for in my width, and then I need to have 2 lengths that are left over. Well, that would mean that my next picture would be, if I took 24 away from everything, that would leave me with 56. And then if I could have 24 feet including for the 140, that means that I would have, let's see, 116 remaining. So that means each L could be a number between 28 and 58. So I hope you enjoyed this kind of exploration. I think it's a really nice demonstration of how, if you allow yourself to just play in the realm of math and figure out how you want to represent things with notation and how that organizes with just numbers in general, when we come back to the real world and we're trying to apply things, we can put something that seemed like it was arbitrary, like real number lines and set building notation inequalities, into context that actually makes us solve these problems in a much simpler format. So really nice work today. Great job working through all of these notes. Let me know if you have any questions.